Okay, so the title of my talk is a computational process of a process-based therapy from relational frames to ideographic graphs. So the whole purpose of this is we want to explore whether we can create ideographic graphs that could be usefully applied within a process-based therapy that's entirely from relational frames. So I know lots of folks want to do process-based therapy and incorporate cognition. I'm exploring this purely from a relational frames component. I've got no problem using cognitive science. I've got a background in cognitive science, so I'm very pro cognition. But here I just want to explore this from a more foundational relational frame perspective. So we know the kind of networks that we can produce if we are told, for instance, Dave is Steve's father, Bill is Steve's brother. You're directly taught two things, and then you can derive four relations. You derive that Dave is also Bill's father, Steve is Dave's son, Steve is Bill's brother, and Bill is Dave's son. So you derive four relations when you're only being trained two. Now, the more frames you're directly taught, you derive a much greater amount. So it almost seems exponential growth. So for instance, if you're taught four frames, Bill is Steve's brother, Dave is Steve's father, Linda is Steve's niece, Emma is Steve's mother. You derive all the things there on the right in blue, the 17 different relations. I won't go through them because there's a lot of them there. So we know there is some kind of exponential function for every new instance of a new relational frame directly taught, and the number of derived relations that are produced as a result of those directly trained relations. So this is what we call the straight line to linear function. The curved line here, this is a exponential function. And I think that's what's going on. I don't believe there's anyone's done any specific work, but I think there's some kind of exponential growth in the number of trained relations. So these networks become very complex, very fast as they grow. Now, there seems to be a bit of a mismatch, a bit of a gap when it comes to RFT and ACT-based concepts. So it almost seems to be they perhaps were constructed almost independently. There's some aspects I can see that connect very well. The Deictic relational frames, here versus there, I versus you, now versus then. This whole perspective taken around the self, I think that clearly is coming from the relational frames. But there's other aspects where it's less clear. It's less clear how cognitive diffusion, acceptance, and contact with the present moment comes through, as well as values and committed action. Now, I would have thought that it has to do with entanglement of thoughts, but I'd like to do further research and explore like potential strengths of relations within the relational network, and actually create maybe weights on those relations. And the stronger the weight is, the greater effect that those weights, those connections carry, and have an effect on overall behavior. As you start to use acceptance and cognitive diffusion, perhaps the strength of these weights decrease. So that's the kind of area I'd like to explore in a little bit more detail, to really understand how these relational frames connect with this middle level concepts in the ACT model. But let's take this one step further. So we know the key property of RFT is this thing called arbitrary applicable relational responding, AARRing, and operant learning, and it's got some very cool features. such as the transformation of function. You're scared of a snake. Someone tells you these snakes are in these woods. You previously have been neutral. You felt neutral about the woods, and all of a sudden now you know these snakes are there. The woods in itself becomes some stimulus for a fear response. So it transforms the woods into something that you're now afraid of. And with self as content, someone arbitrarily says you do something bad, you fall off your ski board or something, so you're something terrible, you're bad, you're a loser, you take it to heart, and then you start constructing with additional language, maybe other instances of this, that you somehow are a failure. It transpires you've developed low self-esteem, and you can see how through an RFT approach that someone could lose confidence if they were constantly told that they were a loser or whatever, as they make those arbitrary frames given certain instances in their life. So we can learn. RFT is good at showing us we can learn how kind of low self-esteem emerges if we get caught up and locked into these thoughts of I'm a failure, I'm a loser, generally called self as content. And this might have categorical decisions making outcomes where if you do have low self-esteem because of this prior history of self as content where you feel like you're a loser, maybe you're not brave, maybe you're too afraid to go into the woods, and that might be fine with the woods. But what if it's something more serious? What if it's like it generalizes and you're now avoiding not just woods, but you're also afraid of what people think of you, and you start avoiding social situations, become lonely, and it kind of generalizes into isolation, loneliness, and so forth. So you can see the RFT model gives a very good kind of general explanation. You can see it's intuitive and it makes sense. Same as high self-esteem. If you're naturally winning and everyone's telling you you're the best, you're great, you might have an inflated sense of yourself. High self-esteem, I think you're the best thing ever, and that might have consequences on your categorical decisions where you might be afraid to go into the woods because there's snakes in there, but you say I'm a brave person, I don't need to be, I'm scared, but I'm a success, I don't need to avoid things, and you might enter the woods because of this high self-esteem that you might carry about yourself. And that might have positive implications that generalizes into general confidence and sociability, and that might be a positive thing. So it's self as content is good when it goes well, and it's terrible when it goes against you, and you start arbitrarily relating bad things about yourself. So the point I'm trying to make here, it intuitively makes sense, and it definitely is touching on something that is very important in clinical work. But we tend to rely on these middle level concepts. We tend to rely on the act based model. And the process based approach is almost a move away from that, where it's trying to develop much greater and precise network dynamics. So the question I'm asking, I've got a mathematical background, can we use more precise mathematics within this kind of area so we are absolutely nailing it with a mathematical kind of precise way of specifying our relations within a network that could be used for PBT research, process-based therapeutic research. So less hand waving and more mathematical precision is the direction I'd like to go down. So just looking at the PBAT is the process-based assessment tool. I really like this. I really think this is a good thing. It touches on things which are value-based. Again, it's difficult to see how RFT and things like values on the ACT model, how they relate. We know values are important. I'd like to see work that connects RFT to value-based stuff. There might be stuff out there, but I've not seen it. So I'd like to see additional work being done there. You can see it's touching on present moment, opener stuff. So it's talking about things that are meaningful, talking about things that are, I was less able to experience a range of emotions appropriate to the moment. So it's like present moment openness. But it also touched on kind of more RFT based kind of concepts like entanglement. My thinking got in the way of things that were important to me. So again, that's importance, that's values orientation, but it's talking directly about thinking. This is like relational framing, arbitrary responding, and rigid rule following. I did things only because I was complying with what others wanted me to do. So again, this is touching on rigid rule following, which is there's work there that's been done in terms of RFT interpretations of that. So I like the fact that it's got these kind of middle level concepts and it's got these RFT types of concepts, and that's where I feel the field should be going down with PBT research. It should definitely be tapping into this kind of more fundamental RFT relational framing kind of thing. So the question I'm asking is, can we develop something grounded purely from these RFT frames that's entirely functionally contextual in nature, and then build that from a strong foundation up into PBT research without having to necessarily anchor onto kind of accurate concepts? So for those who don't know this, I'm just going to say these out just because I want this to be a talk that's applicable not just to a CBS audience, but also to a cognitive audience and so forth. So within the functional contextual relational frame theory, there are several patterns of arbitrary applicable relational responding. I'm going to be calling this RFT from now on, or types of relations, which include frames of coordination, stimuli X the same as stimuli Y, frames of distinction, stimuli X is not the same as Y, frames of coordination, if X occurs, then Y will follow, frames of comparison, X is bigger than Y, frames of opposition, left is opposite to right, frames of hierarchy, Alsatian is a type of dog, and the Deictic relations as perspective taking, which involves some self-reference of the interpersonal relational frame I versus you, the spatial relational frame here versus there, and the temporal relation frames, which is now versus then. So these are the basic RFT type of frames that you get within RFT. And I was wondering, how do we go about trying to specify this within using mathematics, using things like set theory and propositional logic? If it's possible, what are the limitations, and exploring, how far we can get with that, so we can actually formalize through graph theory a concrete model based on set theory and mathematical logic that builds these complex graphs, which I guess you can get into complexity theory and category theory and topoi theory and lots of different mathematical structures. So there's huge scope to do additional work here. So there is a natural relationship between set and logic. For example, if A is a set, then proposition Px equals X. The E there, the backwards E, means belongs to A, is a logical formula of the set which states that a proposition holds for some value of X in a domain or set associated with X. The proposition is therefore true for elements of set A and false for elements outside of set A. I discuss these things in detail in my paper, 2023 paper, Functional Contextual Implementation of an Evolutionary Energy-Based and Embodied Free Energy Framework. So just go through that if you want to go through these in detail. Now, within mathematical logic, there are sub-branches of propositional algebra and predicate logic. A proposition is any type that can be assigned a unique value of either true or false and cannot be both true and false. So in logic, things are true or false. A is bigger than B. Is that true or is that false? Now, you might say it might be true in one context but not another context, and that's absolutely fine. This is why we need to scale up into these more complex graph networks that allow for these kind of transformations. So logic and sets by themselves are very static and limited. It's only when you expand out into dynamic graph networking and explore the complexity within that, that you can have these kind of transformations. So I'm only going to be going through the very basic logical expressions. I'll do another session where I'll go into topoi and category theory and network information theory. But let's just keep it simple for now. So in RFT, derived stimulus relations is a special generalized form of relational responding, and the logic symbol, that's this little arrow here, is literally the logical operator for implies or derives. So you could say, thus, if A is bigger than B, then it can be derived that B must be smaller than A. And that can be expressed as A is bigger than B. A is bigger than B, that's one proposition. And then this implies or derives B is therefore smaller than A. So you can literally use this symbol for derives. The technical word in logic is implies, but derives works well. And as I say, once you get into more complex things, you can actually transform functions, as we're going to get into. Once you can transform functions, then you're getting into RFTing. You're getting into the basis of transforming one function for one stimulus onto another stimulus through these relational frames. So there is much complexity to this, is what I'm trying to say. So relational frames of opposition, mutual entailments. This little L thing is called not. So not A, and this is similar or identical. A is not A. So it's basically, this is just a mathematical way of saying not A. The relational frame of opposition can be defined as A equals minus B. So minus B is basically, that means opposition to B. Or A is the opposite of itself. So A minus minus A, the opposite of itself. This can also be represented using A with the reversed T, which means that A and B have opposite properties, such that A could be true and B could be false, or vice versa. This can also be represented as A. This here means that A and B have some shared properties. So set A and set B have some shared properties, but this ain't equal 0 with a cross to it. That means a null. That means no, there is none. So there's no properties that A and B share. So it depends on how you want to express this. This could be distinction or opposition, and I think you can use those kind of expressions well. So to express the relational frame of mutual entailment of two variables A and B, this can be expressed in set theory as A, and this here means subset of B. So A is a subset of B. This symbol is and, B is a subset of A. So it's implying some mutual entailment between the two. This means that A is a subset of B and B is a subset of A, or more generally, all the elements of A also belongs to B, and all the elements of B also belongs to A, which implies mutual entailment. For example, mutual entailment between the spoken word snake and the concept, or let's say picture, or the actual snake within the real world can be represented as a set, and could look something like this. Verbal word snake is a subset of the actual, or entails the actual snake, and actual snake entails the verbal word snake. So again, you can use these kind of symbols to represent some kind of entailment. So if this subset includes all the properties of this subset and the reverse is true, the actual snake assumes all the properties of the verbal word snake, then they are mutually entailed by definition. Combining elements such as relation in comparison could be expressed as A is greater than B and B is greater than C. So if A is greater than B and B is greater than C, then to complete combinatorial entailment, all you need to do is have this implies or derives. So A is bigger than B and B is bigger than C, derives A is bigger than C. So RFT with causal relational frames. So causal relations. Now you see, I've seen in previous papers in RFT, they like researchers like to use this R symbol, which basically just means relation. There is a relation. Now I've seen some debates on the listservs. You know, is this adequate? You have to specify what the relation. So I do think these things are probably a little bit overly simplistic as they are currently expressed. But I think we can take this a step further and actually say, well, what is this relation? A. So all this means A R B. That means A and B have some kind of connection with some relation R. That's all that's saying. There's some kind of relational property, but it's not telling you what. There's no specification of what is that relation. So you've got to create some kind of function, some function f to map to a set, such as fa equals b. So that's a function A equals B. It's mapping, which means that some functional relation A causes B. This can also be expressed as f A, and then this leads to B, which depicts a function such as A implies B. These functions are mathematical expressions and could include transfer of function. So we could include these kind of functions to even express a transfer of function. Now, RFT in hierarchy. A relational frame in hierarchy can be expressed using set theory, but finding a set of elements where each element belongs to one or more subsets, and each subset belongs to one or more supersets. So we've got supersets and subsets. Subsets are lower in the hierarchy, supersets are higher in the hierarchy. The hierarchy is then defined by the relationships between the subsets and supersets, such as a subset of or superset of. In terms of logic, the hierarchy can be represented using propositional logic statements where each element is represented by a propositional variable, and the relations between subsets and supersets are represented by logical operators such as and, or, implies, etc. So you can expand on these hierarchical relations with these kind of operators. For example, if A and B are subsets of C, such that A equals Alsatian, so A is a set for Alsatians, all Alsatians, B is a set for all dogs, and C is a set of all mammals, then a statement A and B are subsets of C. A and B are subsets of C. All that's saying is Alsatians and dogs are subsets of the superset of mammals. And we know that because mammals are at the top of the hierarchy, and then below that you've got dog, and then below that you've got a very specific kind of dog like Alsatian. So supersets are more broad. And they're more encompassing. They contain the containers of what's below. That's all a superset is. It's a superset. We're using words like animals, but these could be things like feelings. We could have subsets of dimensions of feelings or thoughts or whatever you want to say. But A is a subset of C. I hope that's clear. Can be expressed as A. So we're here now. A is a subset of C, and B is a subset of C, where this symbol here, this side with C, is a subset symbol. So whereas we had in the previous thing with mutual entailment, we just said A is a subset of B and B is a subset of A, expressing a mutual entailment. Here it's a little bit different because we don't have that looping mutual entailment. Here we have the A is a subset of C, and B is also a subset of C. So everything is a subset. Or you could even say A is a subset of B and B is a subset of C. So they're both subsets of this superset, which is a mammal. Alsatian is a subset of dog. So Alsatian is a type of dog. That's why it's a subset of dog. So dog is a superset, and dog is a subset of mammal. So in this case, dog is a subset and mammal is a superset. So more concretely, you could say something like A is a subset of C if and only if for all, that's what the underground. So I'm using logic here. So if this confuses you, this means for all. So I read this like English. but I can understand why it could be difficult if you're not seeing these things. So A is a subset of C if and only if for all x where x belongs to A. So this is an instant of belonging. So this is one Alsatian that belongs to the set of Alsatians leads to x, an instance of belonging to B, which is a dog. So x belongs to B, and B is a subset of C if and only if for all x, x belongs to B leads to x belongs to C. This means that for every element in x in A, it is also an element of B, and for every element of x in B, it's also an element in C. So this is hierarchical expressions. These are hierarchical expressions. Granted, they're very static in the way they're expressed, and this is why we need to go into complex network dynamics, complexity theory, topoi theory, and all these other really complex category theory. Topoi theory is category theory, but it's a set implementation of category theory. I'll do a whole session on that in another time. But these are the general implementations. In other words, A is a subset of B, B is a subset of C, indicating a hierarchical relationship between the sets, with A as the lower subset level, B is the middle level, and C is the highest superset level in logic and hierarchy if of the statements if A then B and if B then C can be represented in that following way, where this here is a logical connective, which means implies. This implies this. So now we're into Deictic, perspective taking type relational relations. And here we are referring to the spatial, here versus there, temporal now versus then, and interpersonal I versus you. These can be represented in logic using quantifiers. For example, the Deictic relation I-U can be represented using four first-order predicate logic quantifiers. For all, that's the upside down A. There exists, that's the backwards E. For example, the statement, I am faster than you, I am faster than you. So I versus you can be represented as for all X, person X implies faster X implies faster I and slow you. So you probably, when I read that, you probably picked up a couple of words there where it basically says fast I and slow you. I am faster than you. So the natural language way of saying it is I am faster than you. The logical predicate logic way of saying it, this sentence here is essentially saying you have to it's got to be constructed in a way. It's basically saying there exists, for all X, persons X. So if you skim through it, this is just saying I am fast, you are slow. I am faster than you. So it doesn't read exactly like natural language, but it doesn't need to. As soon as you identify the meaning within the thing, I fast, you slow. It's almost like a baby shorthand expression. How a baby might express, a 3-year-old or 2-year-old might say, I want this, like incomplete sentences. That's how I read the maths. It's I slow, I fast, and you slow. I am faster than you. This can be read in natural language as for all X, if X is a person and X is fast, then I am fast and you are slow. That's the exact way of reading it out if you were to read it in English. Similarly, the spatial deictic frame there can be represented the same way using qualifiers for all there exists. For example, the following statement, over there is a book on the table, can be represented as there exists, that's the backwards E, there exists book X and on table X. This reads in natural language as there exists an X, such that X is a book and X is on the table. So that's the way it reads. It's basically saying there exists, is the logical way of saying it, there exists an X. And then you've got to define what X is, such that X is a book. So you know X is a book and X is on the table. That's what that thing is saying if you were to read it purely in English. But more simply, you can just say there exists a book there on the table, which is the spatial attribute of the Deictic. This can also be expanded using set theory as shown with other relational frames. in more complex expressions. And we can again expand this using graph theory and information theory. And now we're getting into transformations of stimulus function. In the case of a transformation of stimulus function, where, for instance, you are afraid of snakes, and you're told by an expert that one lives in the local woods, a relational frame coordinating snake with the woods forms. With this coordinating framing, the fear function from the snakes can then transfer to the woods, so that the neutral stimulus of the woods then transforms into a fear-provoking stimuli. So again, a representation of this using set theory can be made, whereby the set of all things you're afraid of, denoted here as f, so f is the function, equals x such that the line there is x such that x is a snake. So all that's saying, x such that x is, it's just defining it. That's what you do in logic. The function is x such that f is a snake, and f represents fear, so that's a fear function. So now we're getting into fear functions, and this is how you can express these kind of things mathematically. And then later we can produce values, and this is the beauty of it. We can create strengths in the networks and values, and you can see how this could be really, really powerful, as you are able to see the strengths of the connections within the networks, how transformations are traveling through the networks in a very, very precise mathematical way. Then as you frame snakes within the woods, this can be represented as a function typically denoted as f. Here is denoted, I'm denoting it by t to distinguish it from other functions, whereby tx equals x equals y, and x is a snake, whilst y is the local woods. The transformation of the function of fear to the woods can then be represented as tf. So that's a function t for f, where f is x such that f is a snake. So f is basically a set, which is x such that x is a snake. So that's basically saying tf is the fear function of snake equals y such that y is local woods. It's just defining y is local woods, and there exists an x is a snake, and tx equals y. So now tx is now implies ty. So the function tx has now transformed to the function ty. So basically, fear of the snake is now transferred to fear within the local woods. Explicitly, this translates to the set of the woods that you are afraid of is the set of all woods that are framed with a snake through the function t. That's the exact way that's defined. I developed some Python code to kind of show you how you would construct graphs. You might specify, you would add a node, snake, you'd add some kind of woods, then you would create some kind of edge connecting woods and snake together. So very, very simple. I've got a GitHub, and you can actually, if you look at the paper, you can actually download some of this code and use it, modify it. I've got to go here kind of explaining that f is a snake. So the function I'm defining def t is defining function tx, whereas x is a snake. So that's basically a function of x. We know that's a fear function, and then add woods. So it's adding woods to that fear function. So it's basically that's one way to compute a fear function for woods, given the t function of x. You can produce this into really dynamic graphs, and I've kind of gone through here. So here's some code for two communities with a resultant community. T there, that's the transfer of function. I can't remember what y x is. This is the function. This is I'm just trying to remember what the things is. Y is the local woods. T is the function, the fear function. X is the snake. So it's basically saying the function of fear that's connecting with the snake, and it's also connecting now with the woods, and it can be connected more generally, but you can highlight these. So there's specific ways you can highlight if you follow that code there, and this would lead on to a community thing, and this might be connected to another network. I haven't drawn it in here, but this is the connection of self. So maybe it starts generalizing. This fear of woods might be generalizing to maybe some concepts about self. So maybe when we were talking about low self-esteem derived from arbitrary applicable responding from history, where you might have learned that you're a failure, a loser. Maybe that allows this kind of fear response of Woods that's now being developed to transpire into other aspects of fear. Maybe you start avoiding people. Maybe it develops generalizes more generally across the network. And this is how these kind of operants can kind of be seen to mathematically spread through the network like a virus. Now, we can look at these kind of SEM models, and we can look at these kind of GIME, these ideographic or vector autoregressor models. So this up top here, this A is your standard structural equation type model. It's very, very static, basically regression. So X relation with Y, relationship with Z, and you might have external variables. And then with the kind of more GIME type autoregressive thing, so this is updating with a time series. So this is basically updating ideographically over time using functional. So maybe you're asking questions like the entanglement of thoughts or things like that. Now these will be updated over time 1, time 2, time 3. So not static like previous SEMs. They can be entirely adaptive. They don't need to follow a latent variable approach. They can be entirely direct measures, or you could construct your own latent things. So the idea is you've got time 1, time 2, time 3, and these all connect to some 1 points. So this could be your actual fear response, and this could be changing fears over time, or could be depression over time, all connected to one point here. You can also have, so this 1 point here could be identified here as this one observed variable, and this could be entanglement with thoughts over 3 points in time, or 6 points in time, or 1,000 points in time. You know, it doesn't matter how far you want to go back. How you want to apply this within your PPT research is entirely up to you. But you could then, given this node, this ideographic multiple time point updating, remember it's updating, like this autoregressive thing here, you could then include a transformational function. So this could be some kind of fear response of a snake. It could transform to your experience with Woods. So progressively over time, you might have more and more fear of local Woods. And then you could incorporate latent variables in this ideographic way, or they could be direct measures. It's entirely up to you. I'll let the user decide. You can incorporate, this is basically T is time. So this is time plus 1. So this basically means at time point 1, and this is basically at time point 2, T plus 1. And you would have T plus 2, T plus 3, etc. B, this is a subset. So B can be expressed as a subset. So you can incorporate these subsets and using set theory within these graph dynamics. All the things when we talk about predicate logic and sets can be now incorporated within these kind of dynamic network graphs. And I will do this in more detail. I'm just giving an overview for this. Basically, this is supposed to be basically a 15-20 minute overview. So ideographic ecological monetary assessments, the kind of RFT time series assessments we could do, we could ask things like, to what degree do you find yourself entangled with your thoughts about future and past events? You know, it's touching into these Deictic type things where you've got future, past, I here, you there, now, then, and to degree to which you're able to connect to the present moment sensations in the here and now, rather than getting stuck thinking about the future and past. So basically this is like PBAT, but it's just trying to tap into more of these kind of specific relational properties rather than linking into the act-based properties. So again, it's up to the user whether you tap into these middle level properties like the PBAT does with values, or more specifically with these kind of relational frames approach, and or mix match it like the PBAT, you know. So I'm just trying to give I'm not trying to say one is better than another. I'm just trying to say there's options here. If you wanted to do a more RFT type approach, this could be one way of doing it with a very, very specific mathematical approach. But you would have to have, like the PBAT, an RFT, a very, very solid RFT kind of questionnaire like the PBAT, but it's heavily based on relational frames as opposed to adding in things which are maybe middle level like act terms. That would be my idea right now. I'd be open to discussion on it, but that's where I am right now. And overall, then we can construct these kind of complex networks dynamics. And this is when I'm talking about graph theory. So we can incorporate things like set theory and logic using these kind of ideographic graphs, building this autoregressive SEM, if you want to call it that, or it doesn't even have to be an SEM, it could just be a pure ideographic graph. And this will tell us very, very specifically using RFTing, using these arbitrary relational frames within dynamic networks, and it will give us a huge amount of precision, and it will be completely driven by RFT, not middle level act. And I think this is the way that we should be, or some of us should be, exploring RFT within the PBT environments. So I don't think we have to focus on cognition. I'm entirely open to cognitive science. Like I say, I've got a background in cognitive science, but I'm just trying to open up some ideas here. Anyway, this is just a very, very quick overview, and I didn't want to go into too much more detail than that right now, but I will go into more depth at a later date. Thank you very much. Please look at that paper that I mentioned, my 2023 paper, if you want to see the kind of mathematics in more detail. Thank you very much.